Welcome to this new lecture, which is about dimensionality reduction. So, dimensionality reduction is the process of reducing the number of features in a dataset while still preserving as much as information as possible. And so, the number of features can actually be reduced in two ways. Number one, using what we call feature extraction, and it's the process of combining features to create new ones. Or we can reduce dimensionality using feature selection, which is the process of selecting a subset of features from the original ones. And so the primary goal is to simplify the data representation and try to make data more manageable and enhance interpretation. It does also reduce computational cost, which is very important when working with large data sets. And so dimensionality reduction is a very important step in the data pre-processing pipeline. As you can see here in this figure, imagine you have a data with hundreds and thousands of features and you would like to visualize a scatter plot of your data. Then you do need dimensionality reduction to go down to 3D or a 2D feature space. And so in this lecture, we will focus more on the first method for dimensionality reduction, which is feature selection. So there are multiple types or categories for feature selection methods, and they generally fall under three broad categories, which is filter-based, wrapper-based, and embedded-based methods. So with filter-based methods, the idea is to rank the features based on relationships between between the input and the output features using some statistical measures such as the Pearson correlation coefficient, the F statistics, the chi-square statistics, and so on. On the other hand, with the wrapper methods, the idea is to select features by iteratively building and evaluating models on a subset of features. And so you select features based on each feature's performance, right? And a common method which we'll discuss is the recursive feature elimination, which only retains and re-evaluates models under a set of number of features remaining in the set. And so lastly, we have the embedded methods, which actually integrates the feature selection process into the training of the model itself. And so the feature selection is actually performed in parallel to model training rather than iteratively or sequentially. As an example of models that do that, lasso regression and random forest, they do perform embedded feature selection method. And so, as we said, the first type of feature selection method is filter-based, and we said that these methods select features according to a statistical measure. So in this example, we are ranking features and we are calculating their corresponding F value and a P value, and then the 5 features that have the highest if statistic value, then the others are selected. And so you can see if we select the best or the highest features that have if we select the best features that have the highest F statistic value, which turns out to be 5 features here, then the model will perform better and will score at 90% accuracy, versus if we did not perform feature selection and used all our inputs, then the model would only score 88%. So this shows the importance of feature selection in improving the performance and the predictive power of our model. So here I'm showing some common filter-based functions in Scilern that you can use for your project. And so functions like select k-best and select percentile. So for select k-best, it removes all the features except the k-best scoring features, and the select percentile removes all features except the highest scoring percentage of features defined by the user. And so you can explore these two functions along with their parameters and try them on your final project models and see if the performance gets better. Now to the second type of feature selection methods, which is wrapper-based methods. A common wrapper-based method is recursive feature elimination. The idea is to iteratively remove the least important features from the data set until a desired number of features selected by the user is reached. The recursive feature elimination algorithm takes in two hyperparameters, an estimator and the desired number of features. So this figure explains the steps of the sequential feature selection algorithm. So you train the model using all your initial P features, and then you rank the importance of each feature. And so suppose that feature 2 was actually the least ranked feature, then this feature will be removed, and then the remaining p-1 features from the first iteration are used to retrain the model again. And then in the second iteration, we perform the earlier steps for the remaining p-1 features and so on. So the algorithm iterates until we are only left with the desired number of features. So sequential feature selection removes features from the data set using a step-by-step manner, and also using cross-validation technique to evaluate the model performance at each one of the iterations. And there's two main types of sequential feature selection. There's forward search and backward search, or forward and backward selection. And so although these two may sound the same, they actually yield different results. So with the forward selection, you start with no features and you keep adding features to the model, starting with the most important feature and so on. On the other hand, for the backward search or the backward selection, you start with all your feature set and then you iteratively remove features from the model, starting with the least important feature. So once a feature has been removed or added, you do that for good. So once a feature is removed, you cannot add it back again to the set. So this figure explains the concept of forward search or forward selection. So you begin with an empty feature set and then you sequentially keep adding features in each iteration, and then you train the model and evaluate it using the one feature subset. And then the one feature subsets, because you're going to end up with multiple subsets, each has simply one feature, and then the feature that will yield the best score, it is added to the candidate feature set for the model. And so, for example, if we assume that feature 2 here was the one which yielded, right, feature 2 was the one that yielded the best score, then this feature will get added to the candidate feature set, and then in the next iteration, two feature subsets that contain feature 2 and another feature are used to train and evaluate the model. And so you're going to test feature 1 with feature 2, feature 2 with feature 3, feature 2 with feature 4, and so on. So all the way to, you do that for all the other P features. And so the algorithm sequentially adds features to the candidate set in the same manner. And so the subsets features are that actually give the best score will be selected for the model. And so the backward selection, on the other hand, works in the opposite direction. So it starts with all the features in the data set and then sequentially removes features in each iteration. And so if we assume that initially the features 2 all the way to P are the best performing features, then feature 1 will be removed from consideration and will be removed from the candidate set. And then in the next iteration, we are only considering feature 2 all the way to P, and the process starts again. So the algorithm will sequentially remove features from the candidate set, and then the subset of features that give the best score will be selected for the model. And so again, these are the functions that you can use if you want to try to experiment the feature selection for your final projects. So there is the RFE and the RFE CV, which the version that performs cross-validation in each iteration. And then you do have different parameters that you can experiment with. And there's also the direction parameters where you can determine if you want to do the forward or the backward search. And so the last type of feature selection methods is embedded methods. So this type of feature selection method selects the most relevant features during the model training phase. And so they're different from filter and wrapper based is that they are an integral part of the model building itself, right? So they typically incorporate feature selection as a step within the algorithm or the model training itself, right? And so you do not need a separate step to perform feature selection, right? It's already embedded in the model training itself. And so in summary, all three feature selection methods, they do begin by loading a data set with all your input features. And then these features, so you can call these the feature space initially. And then you have the filter-based methods, which select a subset of the features before model training, right? And then the wrapper methods follow this iterative approach that loops between subset selection and model training. So you select a subset and then you train your model, you get a score, you compare it, and then you select another subset, you train, you get a score, you compare, and so on. With the embedded methods, this is the most efficient one because with embedded methods, you are incorporating subset selection, model training, and model evaluation into one single phase, one single algorithm. You do all three at once. And so the second type of dimensionality reduction, so we spoke before about the first type, which is feature selection. The second type to reduce dimensionality is feature extraction. So this process creates new features from raw data in order to both reduce the dimensionality and also identify important patterns. And so feature extraction can lead to improved model performance, reduced training time, and better generalization to new data. So there are multiple methods to perform feature extraction, and the linear ones are actually taking combination of existing features instead of using all of the original features. And among the linear feature extraction techniques or methods, we find PCA, or also called principal component analysis. There's also independent component analysis and factor analysis. So we're not going to be covering these in this course, but there's one last chapter or section in Zybooks about PCA if you are interested in knowing more about the theory behind it and how to implement it.